All right, so we're going to wrap up this unit by talking about fundamental forces. So, we've talked about forces ever since Unit 3, and we've talked about, well, you've got your normal force and your tension force and friction force and applied force. But honestly, all these are just different manifestations of one force. It turns out in the universe, there's just four forces that exist, and two of them, although they're part of your life, you never really have a chance to actually see them in action directly. There's just two forces really that you directly are aware of. So let's just go ahead and take a look at this. So there are four forces in the universe, at least according to the standard model. And these four forces are the strong nuclear force, the weak nuclear force, and sometimes they say the strong and weak interaction, but we'll just call it forces, the gravitational force, and the electromagnetic force. Now, it turns out the vast majority of the forces that you think of are manifestations of the electrostatic force. Now, we say electromagnetic force. For a long time, people thought there was magnetic force and there was electrical force. And then they came to realize, say this quite a bit in AP Physics 2 when you take it, that electricity and magnetism are just different manifestations of the same thing. But realistically, most of the time that we interact with matter, we're really interacting it in terms of the electrostatic force, so the electrical force. But we'll call it the electromagnetic force. But there's just those four forces. That's it. Okay. So let's just go through each of these in turn and see, what we need to know about them in terms of the AP test. So we'll start with the strong nuclear force. So the strong nuclear force basically is, as the name implies, it is what holds the nucleus together, both in terms of the particles within the nucleus and between the particles that collectively make up the nucleus. So if you're aware of this or not, there are what are known as quarks. So quarks are these particles that are bound together, three quarks together, either up quarks and down quarks. There's actually six, but there's two of them that are involved in making um, protons and neutrons, and so there's up and down quarks, and so you have three quarks together that make up a nucleon, a proton or a neutron, and the strong nuclear force binds them together. And so we won't get into the detail of the different particles go between them to hold them together. We'll just say what it does basically is it binds quarks together to make nucleons, to make protons and neutrons, and antiprotons and antineutrons. Not that we have to go there, but also there's sort of like this leftover amount of force that can then hold protons and neutrons together. So it can also, in addition to holding the quarks together within a nucleon. So this is supposed to be like a nucleon, and here are different nucleons that are being held together by this strong force. So that's what it does. So yes, it's a part of your life because pretty much every atom in your body has to have these forces working within it, but it's not something that really we see in action. Now we have the weak nuclear force, and the weak nuclear force is responsible for the decay of nuclear particles. So, for instance, if you have a neutron and it's not in close proximity to a proton, in a very short period of time, it will decay and become a proton. And the way it does that is by emitting an electron. So, right now I have a neutral particle, it emits an electron. And now, since negative charge left, this charge is something that is conserved the same way that energy is. Uh, and this will have to then become a proton. So basically, it is a force that causes the decay of particles. So unbound neutrons become protons because of this. Also, in the sun, individual protons can be packed together, and in which case, or the opposite happens, a proton can then become a neutron. And they do that by what's called electron capture. So in electron capture, a proton absorbs an electron and then becomes a neutron. So in all of these cases, it is the effect of the weak nuclear force. Now, the strong nuclear force and the weak nuclear force do not follow inverse square laws as the other forces do. They operate over much shorter distances than that. So the distances across which they work are significantly less than the diameter of a nucleus. So these are very, very, very short range forces. That's why you don't directly notice them. They're important. They do affect your life. You just don't notice them. You don't feel them. Let's talk about the ones you do and the ones that really are going to be the focus of the AP test questions. Start with gravitational force. Okay, so the gravitational force is actually the weakest of the four forces, but it's the one that wins out in the end. It's what binds the whole universe together. It is an awesome force, right? It builds up. It makes these really strong piles of atoms have these big gravitational pulls. But because G is such a vanishingly small number, remember 6.67 times 10 to the negative 11th, it's very weak. But here's the thing: it can work over long distances. It is what we call an action at a distance force. But what's most important, the reason it ends up winning overall, in a sense, that it is the dominant force in the universe, even though it's the weakest, is because it only attracts. There's no repulsion component of it. It basically there's nothing you can put in the way of it to shield it. It reaches through everything. It pulls everything together, and as we remember, it's defined by the equation: the force of gravity is equal to the gravitational constant times the product of the two masses of the objects interacting gravitationally divided by the square of the distance between their centers. The reason I read that to you is because I want you to look at the next one, the electrostatic force, or we'll just call it electromagnetic force. So electromagnetic force is the strongest of all the forces, and it too is an action at distance force that can act over quite large distances. Now, one way that is different from gravitation is that it has both positive and negative charges, so it can both attract and repel. If I have two positive charges, they will repel each other. I have two negative charges, they will repel each other. And if I have a positive and negative, they will attract each other. And as a consequence of that, like for instance, the chair I'm sitting in, the table this is resting on, the sum total of all those positive and negatives is such that the table is overall electrically neutral, and so is the chair, and so am I. And since it tends to cancel out, it doesn't exert itself over large distances often, so we don't really notice it the way we do with gravitation. But check out its equation, and it's going to be striking how similar it is. The electrical force is equal to a constant we call the electrostatic constant, uh, which is equal to charge 1 times the product of charge 1 times charge 2 divided by the sum of the square of the distance between those charges. It's the exact same equation as gravitation. It's creepy how similar it is. What's different, though, is this: these can be both positive and negative. If they both have the same charge, this will be a repulsive force. If both of these have opposite charges, it will be an attractive force. And K, when we look at it, is quite different from what it is for G. So put the two equations side by side. It's just mind blowing how similar they are, which makes it easy to learn actually. But let's look at the difference between G and K. So G is this vanishingly small number, 6.67 times 10 to the negative 11th. So it means that the gravitational force between objects is going to be really small unless there's a whole lot of mass involved. Whereas the electrostatic constant is a very large number, 8.9 times 10 to the ninth, not negative ninth, but ninth. It's an incredibly huge number. And that's why we say that the electrostatic force is the strongest of all the forces. But because it both attracts and repels, it tends to cancel out, and it doesn't tend to cause any long distance observable phenomena the way that gravitation does. It doesn't pull comets towards Earth the way that gravity does. But because gravitation is only attractive, that's why we notice it doing these amazing things, causing, Galaxy A, which is, a million light years away from Galaxy B, to fall towards each other because there's no counteractive force component to it. Now, let's look at the different manifestations of the electromagnetic force. So let's say the tension force. Well, what is the tension force? Well, the tension force is basically the electrostatic attractive force between the protons in an atom here and the electrons in the atom here. They tend to pull on each other. And so if I pull this atom here, it wants to pull on that one there. Really, what's happening when you pull on a string or a rope, it's simply atom A pulling on atom B using the electrostatic force. Protons in one atom pulling the electrons to the other atom. Same thing with a spring force. With a spring force, I'm trying to push them together, and the electrons in this atom are repelled by the electrons in this atom, so they don't want to occupy the same space, so they push each other away. The normal force is basically the electrostatic repulsion. As one object here, is trying to push in this one here, the electrons in this one and electrons in this one repel each other, and they hold each other apart. Friction is basically the same thing as well. It's the electrostatic interaction between the atoms, the electrons of the atoms on the floor, and the electrons of the atoms in the object that's moving across the floor, if that's where a static force is being applied. All of these forces are just different manifestations of the electrostatic force. Let's just zoom in on a couple of them here. So for the normal force, basically, I have electrons in the floor are pushing up on the electrons in the box, and the electrons in the box are pushing down on the electrons in the floor. So in actuality, no objects ever really touch each other. And that seems kind of weird, but it's true. So you think, oh, well, my fingers are touching. Well, actually, they're not. The repulsive force of these electrons and the two things won't let that happen. It feels like they're touching, but they're really not. They can't because of this repulsion force. And remember, it's an inverse square with distance. So as they get closer and closer, closer together, that repulsive force becomes quite significant. And the friction force is a similar thing. If this box was just at rest, then atoms here be wiggling, atoms here be wiggling, and they'd be pushing each other in random directions, which would sum to zero. And that's why the box doesn't go anywhere. But if I start to push the box in one direction, then what happens is these atoms are trying to go this way, and these atoms have electrons, and they're like, well, wait a second, I don't like your electrons coming, so I'm going to push you that way. And as I push you that way, you push me this way. So friction, again, is just another manifestation of this electrostatic force. Okay, so thanks for watching. We're really getting close to the end of physics here. I'm looking forward to it.